Next bit, in terms of the movement of electrons, how you get magnesium bromide from magnesium and bromine. So when you have magnesium reacting with bromine to give you magnesium bromide, this is a giant metallic structure. Should probably spell it out correctly. Giant metallic structure. This one is a simple molecular structure. This one is giant ionic structure. Alright, so what is essentially happening? You have gone from magnesium 0 oxidation state because it's an element. This is bromine 0 because it's also an element in this form. This is magnesium plus 2. This is bromine minus 1. So you have done a redox reaction there. The Mg loses 2 outer shell electrons to form Mg2 plus. There's actually oxidation. The Br2 gains, well, you can think about gain the 2 electrons, but each Br therefore gain 1 electron. So you have 2 bromine there. They gain the 2 electrons from the magnesium 2 plus that you lose after the magnesium lose the electrons. But you have 2 bromine, so each bromine actually gain only 1 electrons, forming Br minus times 2. You have got 2 bromide ions. Mg2 plus 2 Br minus form the giant ionic structure of MgBr2. That's how you get the MgBr2 from the transfer of electrons from the magnesium that lose the 2 outer shell electrons to the bromine molecule, getting the 2 electrons forming the 2 bromide ion. Physical property, so it's an ionic compound. It has very high melting point. Electrolysis. So up next, they tell you it's a simple molecular substance. They want physical, they don't want chemical, yeah? So the most common physical property is to do with melting and boiling point. So what I can say is it will have a low melting and boiling point because of the simple molecular structure. Okay, what else can I tell you about the physical property? Well, we can talk about solubility and we can talk about electrical conductivity, okay? So low solubility, or does not dissolve, I guess, in water. All right, so low solubility in water. Okay, you can think about it being a non-polar molecule as well. So it's not going to interact with water. So that's why it's low solubility in water, or just insoluble in water, to be honest, I can tell you. All right, you can also talk about electrical conductivity. Apart from graphite, which conducts pretty well, even though it's a non-metal, okay, because it's got the free electrons on the carbon, most non-metals generally just do not conduct electricity, yeah? So we're going to talk about this compound, which is essentially calcium 2 plus and PO4 3 minus. So when you do the LCM of 2 and 3, you will find out that the LCM is 6, and that's why to get to 6, you need 2 times 3. To get to 6, you need 2 times, well, you need 3 times 2. That's why you have 2 of the phosphate and 3 of the Ca2 plus. All right. So you can tell that it's a giant ionic structure, yeah, because it's an ionic compound. So Ca3PO4 twice has a giant ionic structure. And you will have done polyatomic ions. Polyatomic means many atoms, more than one. Okay, you have done this kind of ions as part of your getting to the formula of a compound. You have done these polyatomic ions like sulfate is SO4 2 minus, nitrate is NO3 minus, etc. etc. Yeah? So when we have a giant ionic structure, when we talk about melting, so melting it refer to melting calcium phosphate would require, what are you breaking? Okay, that is very important. You are breaking strong. You cannot say many because you cannot count ionic bonds. The only bond you can count is covalent bond, okay, because it's directional, whereas things like metallic bonding and ionic bonding, they are not directional. They are like a force field, yeah? So you cannot count something which is like a force field, yeah? So breaking strong ionic bond, that is not enough really. You got to specify for your example, which in this case is between calcium 2 plus and PO4 3 minus ions. And because this requires breaking strong ionic bond, so this involve high or large amount of energy. So we're going to relate it to the energy required, therefore high melting point. All right. So there are two things to the next part of the question. Okay, so we know that solid CuSO4, when they exist as this kind of regular ordered lattice structure like that, the solid CuSO4 has no free moving ions. So meaning to say, you can say no mobile. So free moving would mean that it's mobile. Mobile would mean that it can move around. Okay, so no mobile ions. I don't talk about electrons because when you have ions, the electrons get transferred from the anion to the cation. So you don't really have electrons floating around. You're not talking about metals, okay? So no free moving ions, no mobile ions to conduct electricity. That's why it doesn't conduct. But in aqueous solution, so once it's dissolved, aqueous meaning in water, that means you have this and water, you have a mixture, okay? In aqueous solution, which is a mixture, it's no longer pure. The copper 2 plus aqueous and SO4 2 minus aqueous are free to move. Or you can say are mobile. Therefore, you can carry current. Therefore, you can conduct electricity. Yeah, okay. It allows, well, you know, you have ions now that enable you to move around. Yeah. Solid ammonium carbonate does not conduct electricity, but aqueous ammonium carbonate does conduct electricity. I think I just outlined to you. It is actually ionic. Okay, so it's all down to the ionic structure. So you gotta explain these two observations. Okay, so two observation means you gotta explain one by one. All right. Ammonium carbonate has giant ionic structure. Very important, yeah, structure and bonding. Okay, so in the solid state, the ions are not free to move because they can only vibrate about their fixed position, right? Only vibrate about their fixed position. This is solid we are talking about. So there's no free ions at all, therefore cannot conduct. All right. Whereas in aqueous state, the ions are mobile, therefore they are free ions. They are free ions to conduct electricity. So this is the idea of ionic compound, but they just give you a strange ionic compound which contains the ammonium salt, okay? In this case, ammonium carbonate. Next bit, solid ammonium iodide does not conduct electricity. Aqueous ammonium iodide conduct electricity. Explain these two observations. So you got to explain both of them, yeah? So NH4I, which is the correct formula, in case you're wondering. NH4 plus and I minus, NH4 plus and I minus, that's why it's NH4I, has giant ionic structure. So conduction of electricity is to do with structure and bonding. Yeah? In the solid state, so as a solid, the ions NH4 plus and I minus are not free to move. So if they are not free to move, therefore cannot conduct electricity. Alright, but in aqueous solution, so now you have aqueous solutions. What am I going to say? In aqueous solutions, the ions are mobile, free to move. They are more disordered. Remember, when you change from solid to aqueous, this is not liquid, but you are in water. So you have NH4 plus, I minus in water, so it's a mixture. This is a mixture. Okay, this is pure ionic compound. When they are free and mobile to move in the aqueous solution, therefore can conduct electricity because of free ions. Free mobile ions. Actually, it's kind of repetitive. I'm sure once you say mobile and free to move, therefore can conduct electricity, that will be fine already. Okay. Up next, question 8. So explain why solid carbon dioxide does not conduct electricity. This is a molecule. As a solid, even as a molecule in the gaseous state, it does not conduct electricity because there is no free electrons at all. Yeah, there is no free electrons, no delocalized electron in CO2. Therefore, cannot conduct electricity. Okay, so the electrons have all been used up for bonding here. 1, 2, 3, 4. Next bit, balancing equation. The easiest bit to balance is probably the phosphorus. Well, hang on, when I say the phosphorus, I mean I could start off from the phosphorus. Okay, that's better. So if I have 1 there, then I'm going to have 2 phosphorus. So I'm going to have 2 phosphorus. So phosphorus is done. But because of that, this is tricky. That is not good. You see there's 5 oxygen there. 5 oxygen there. So that means there are 5 oxygen altogether. That means to get 5 oxygen, I need 5/3. That is not going to be a good number. So maybe not that. Maybe I don't start from phosphorus. Maybe I can think about okay, you need a number there. This is going to be oxygen. Yeah, 3 times something must balance something times 5. So for oxygen, you need to balance 3 and 5. I'm doing the lowest common multiple, something you will have done in primary school mathematics before you go to lower secondary, which you do again, lowest common multiple, and now you do again in O-level. So the LCM is going to be 3 times 5, which is 15. This is for oxygen. How do I go from 3 oxygen to 15? I multiply by 5. So I put a 5 there. How do I go from 5 oxygen to 15 oxygen? I put a 3 there. 3 times 5 is 15. So 3 there. Okay, so now the oxygen is balanced. 5 times 3 is 15. No oxygen. 3 times 5 is 15. Phosphorus is the next one. 3 times 2 is 6. So I should put 6 there. The last one to be balanced is the chlorine. 5 times 1 chlorine. So there should be 5 there. And guess what? The potassium just balanced out. 5 km, 5 km. Okay, nice and easy there. Deduce the molecular formula. So total up the phosphorus. 1, 2, 3. Total up the hydrogen. 1, 2, 3, 4, 5. Total up the oxygen. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There you go. Draw a dot and cross for phosphorus trichloride. So I always like this kind of question by thinking just about group 15, and then phosphorus chlorine is going to be a single covalent bond. In each of these there are 2 electrons shared, one from phosphorus, one from chlorine. So when you think about ammonia, you know ammonia is like that, right? Yeah. So phosphorus is in group 15. When you bond it to 3 chlorine, it's going to look similar. What have I done here? Chlorine, just like hydrogen, they form one bond, but hydrogen has no other electrons apart from the electrons it used to form covalent bond. Chlorine, when you form one covalent bond, you still have 1, 2, 3, 4, 5, 6. Because it has 7 outer shell electrons to begin with, it just used 1 for forming covalent bond. This is called display formula. These are not dot and cross. Why did I draw this? I can check my diagram is correct. I know this is 2 electrons. So if I do cross for phosphorus, so that means dot for chlorine, I should have a cross and a dot, a cross and a dot, a cross and a dot. Now I can start drawing my dot and cross. Okay, phosphorus is in group 15. 1, 2, 3, 4, 5. Single covalent bond, single covalent bond, single covalent bond. Okay, this is wrong. Draw all outer shell electrons. This is the most common mistake. Here, display formula does not show all the electrons. They are not used for bonding. Chlorine is in group 17. It has 7 outer shell electrons. 1, 2, 3, 4, 5, 6, 7. Okay. So complete for all of the chlorine, and that's it. Nice and easy. Okay. Next bit, the one on structure and bonding. So white sulfur dioxide has a low melting point. So SO2 has a simple molecular structure. So this is how you tackle this kind of question involving structure and bonding, involving volatility, involving melting point or boiling point. Simple molecular structure. Melting SO2 requires breaking only weak intermolecular forces between the SO2 molecules. Because you're only breaking weak intermolecular forces between the molecules, therefore low melting point.